Welcome to Lecture 5.4, Adjoints. Early on, and throughout this course, I've been preaching the idea that we should be thinking of linear scalar functions, elements of the dual space, as row vectors and ordinary vectors as column vectors, because intuitively, every element in the dual space L can be realized by simply taking the dot product with some fixed vector. So for example, L of x, if we think about x as a column vector, C1, C2, up to Cn, with respect to a basis, of course, we can think about L as a row vector, A1, A2, An, and then L of x is just A1, C1 plus dot, 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 An, Cn. And so this is why we like to write this using so-called scalar product notation, L comma x. Now remember, this is a bilinear function, and we wrote this before we ever defined the notion of an inner product. And technically this is not an inner product because L is in the dual space and x is in the ordinary space x. In the previous lecture, we generalized this idea to arbitrary n-dimensional inner product spaces. Specifically, every element in the dual space can be expressed as the linear function that results from taking the bilinear inner product and plugging in a fixed vector y into one of the two entries. If we're working over the real numbers, this is symmetric, so it doesn't matter which one, so I will stick it into the second coordinate. This canonically identifies a vector space with its dual via the isomorphism that sends y to the inner product of some vector with y. Let's compare two examples of this so we can understand it better. I'll start with R2 and the standard dot product, which we all know and love. And we'll also look at R2 with this non-standard inner product that I've showed you before, defined by the inner product of x and y being y1, y2 times the matrix 2, 1, 1, 2 times the vector x1, x2. So if you write this out, it's not hard to check. This is 2x1, y1 plus x1, y2 plus x2, y1 plus 2x2, y2. Okay, so let's start by looking at what the vector E1 gets mapped to under this identification. So first with the dot product, E1 gets mapped to the linear function that just picks off the first coordinate. So taking the dot product of E1 with x1, x2 just picks off that first coordinate. So I'm going to write this. I don't know if this is the best way to, I'm not a big fan of writing a map to a different map, but I'll try this. So maybe it's better to say that E1 gets mapped to the linear function which pick off the first coordinate. And then, of course, E2 gets mapped to the thing that picks off the second coordinate. Let's compare what these things get mapped to under this identification with this inner product. So E1 down here is 1, 0. And that gets mapped to the linear function that, let's see, when y1 equals 1 and y2 equals 0, then these two terms go away, and we are left with these two. And if y1 equals 1, then this gets mapped to 2x1 plus x2. So in other words, under this identification, this vector 1, 0 gets mapped to the linear function which takes 2 times the first coordinate plus 1 times the second coordinate. So, in other words, the linear map, how do I want to write this? Blank dot 1, 0. So, under this identification, this vector gets mapped here, is equal to blank dot 2, 1 with the standard dot product. So under this identification, 2, 1 gets mapped to the same element of the dual space that 1, 0 gets mapped to under this identification with this inner product. Now, let's consider a linear map, A, between two real inner product spaces, X and U. Recall that the transpose of A is a linear map that goes backwards between the dual spaces, that is, from U prime to X prime, satisfying the following basic property, that L of AX equals A prime L of X. So just this on its own is fairly unmotivated, so you really need a picture, which I'll provide shortly. But that said, when you prove properties of the transpose and when you use it, this is often what's needed. So anytime you have an A in the right-hand side, if you want to move it to the left-hand side, you have to put a prime in front. Here's that picture that I think makes transposes very intuitive. If you haven't watched my prior lecture on transposes, please do that now, because I will go over pictures like these in more detail, and I'll also prove some basic results on transposes that have analogs for adjoint maps, and some useful techniques which I will not be using in this lecture. So the transpose literally is the map that sends this L to this M. So if we have a linear scalar function on U, there's a natural way to send that to a linear scalar function on X just by precomposing it with A. So in other words, A prime sends L to L of A, and we'll call that M. Now, if we identify X and U with their duals via the natural map that sends an element Y to, I'm going to call this blank dot Y, even though it's an inner product, not necessarily the dot product, then the transpose, which, as we said, maps L to M, defines a natural map between the vectors U and Y. This is called the adjoint of A, and it's denoted A star. The key idea here is that given a linear map A from X to U, the transpose A prime is a map between the dual spaces U prime and X prime that maps this L to this M independent of any inner product structure. Whereas, in contrast, the adjoint map, A star, goes from U to X. It maps U to Y, specifically this U to this Y, and this depends on the inner product structures put on X and U. So if we change the inner product, then these linear functionals correspond with different vectors here. Now, if you open any book and look at the definition of the adjoint map, it's not going to give you this diagram. It's going to give you a very clean algebraic definition involving inner products, much like the formal definition of the transpose map. But like the transpose, I strongly recommend that you use this diagram, you think of it this way. While it's convenient and often useful to use the algebraic definition, this is where the intuition really lies. Here is the formal definition. Let A be a linear map between real inner product spaces. The adjoint of A is the unique linear map a star from u to x such that the inner product of ax with u, notice that is happening in the vector space u, is equal to the inner product of x with a star u. Notice that's a different inner product, which is happening in x. So it may not be clear right away why this algebraic definition is equivalent to this diagram that I gave you, saying that a star literally maps, I should say a prime maps L to M, so a star maps U to Y. But I think if we understand it element-wise, something that I put in the previous slide but didn't really go over, it will make this connection more clear. So let's do that. Let's start with x and map it to ax down here, and then see what happens when we apply L and when we apply M, which is the transpose A prime L. So when we apply L to ax, we are literally plugging ax into this first coordinate. So we get the inner product of ax with u. Now, when we apply, and that has to be the same as if we apply m to x directly. And what is m of x? That is plugging x into this first coordinate. So that is the inner product of x with something else. So what is that something else? That something else is, that's y, that is a star of u. So that literally is a star of u. So in other words, this is equal to inner product of x with a star u. And notice why a star is a linear map, because if I replace u down here with, say, 2u, I double it, then in order for this equality to hold, I have to replace y with 2y. So y depends linearly on u. Next, we have a multi-part proposition, which should look very familiar because we did something just like this for transpose maps. And indeed, if you replace these stars with primes, the same results hold. And the proofs are pretty much the same too. You basically just take A and move it to the other side of the inner product and put a star in front of it. So if A and B are linear maps from x to u and C is from u to v, now these are real inner product spaces, then the adjoint of A plus B is the adjoint of A plus the adjoint of B. The adjoint of CA is the adjoint of A times the adjoint of C. If A is bijective, then the adjoint of the inverse is the inverse of the adjoint. The adjoint of the adjoint is the original map itself. And finally, the matrix representations of A and its adjoint are transposes of each other. So just to get you started on how this is going to work, I'll leave this as an exercise, but let's look at the first one. So let's take y is A plus the adjoint of A plus B equal, or y is the adjoint of the sum equal to the sum of the adjoint. Well, let's take A plus B x, the inner product of this with u. So we can write this as ax, inner product of ax and u, plus the inner product of bx and u, and then we can individually write this as the inner product of x and a star u, plus the inner product of x and, that should be b star u. And then since this is linear, we just recombine it to be the inner product of x and a star plus b star times u. And that's that. So all of these basically work the same way, or at least the first four of them. You follow your nose, you write something down, and you move the a's and the b's and the c's to the other side and put stars in front of them. I guess the last one's a little bit different, but I did pretty much the same thing for transpose maps. I don't think it was actually in the lecture for transposes. It was in a later lecture when we talked about the matrix of linear transformation. I showed you that the matrix of the transpose is of the transpose map is indeed the transpose of the matrix of that map. So go back and check that out if you want to see how this is done. It's the same thing here. Finally, I want to finish with a few words about adjoints and the so-called four subspaces, which is a topic of a previous lecture. So go back and check that out if you haven't already. And I'll call this proposition 5.8 and leave most of this as homework. If A is a linear map from X to U between finite dimensional inner product spaces, then the null space of A star is the orthogonal complement of the range of A. The range of A star is the orthogonal complement of the null space of A. The null space of A is the orthogonal complement of the range of A star. And finally, the range of A is the orthogonal complement of the null space of A star. So algebraically, this looks just like, it's a big mess. It's hard to figure out what this is really saying. But together, this tells us that the domain X is the orthogonal complement of the range of A star and the null space of A, or in matrix language, the orthogonal complement of the row space is the null space. And the codomain U is a direct sum of the range of A and the null space of A star. Or in matrix language, the orthogonal complement of the column space is the left null space. Now this holds not just for real valued matrices, but also for complex ones as well, though it's slightly different because the definition of a complex inner product involves a complex conjugate, because the norm of any vector, inner product of it with itself, has to be a real number. Okay, so remember the picture that I've drawn for this is if we have a, so again, I strongly recommend that you go back and check out my lecture on the four subspaces if you have not already. So this is the picture that Gil Strang uses, I really like, is if A goes from X to U, then down here this is the null space of A, and this is the range of A star, and these are orthogonal. And then over here we have the range of A, this is the column space, is orthogonal to the left null space, which is null space of A star. Now I will leave the proofs of these for the homework, but I will say we proved the first one of these in the language of transposes. So we proved that this is on that prior lecture on transposes. So the range of A star, said, was the annihilator of the null space of A. Remember that the annihilator, before we talked about inner products, was the set of linear functionals or covectors that vanished on this subspace. One thing I did not show, but I guess I'll leave as an exercise as well, is that under the identification of a space with its dual, that is sending y to blank dot y, the annihilator of any subspace gets sent to, or the orthogonal complement of a subspace gets sent to the annihilator of the subspace as we defined it previously. So my proof of this in a prior lecture basically carries over line by line because I use scalar product notation. If you just call that an inner product, it carries over for this, and then the other three parts just follow from this. So if you apply perp to both sides, to part B, let's see, you get part C, and then it's not too hard to get part A and part D from this as well. So I will leave that on the homework. Okay, coming up at the next lecture, I will talk about the matrix A star A, which if you've taken an applied math course or a statistics course, you've likely seen the matrix A transpose A. This comes up all the time, and one of the key properties is because it has the same rank as the matrix A itself. So we can actually express orthogonal projections in terms of this matrix, and one of the most popular applications of this is to the least squares method. This is something you've likely seen in some science course. If you have some data and you want to find the best fit line, it what it does is you find this line that minimizes the sum of the squares of the error, but what's not necessarily shown the first time you see this is that what you're basically doing here is the orthogonal projection onto a subspace, and you can express that with this matrix A star A. So stay tuned.